In the beginning of the last video, I mentioned that energy can neither be created or destroyed. This turns out to be a law. Energy can only change from one type to another, and the total energy in our universe is constant. We can apply this concept to help us solve problems. For example, if you lift a book up in the air at a certain height, it has a certain amount of gravitational potential energy based on its height and its mass. If you let this book go, the book will fall and start converting its gravitational potential energy into kinetic energy as it picks up speed. But the whole time, total energy is conserved. Well, let's do an example problem. Let's take a car of mass 1,200 kilograms and roll it down a ramp starting at height 20 meters. The question is, how fast is the car going to be moving when it reaches the bottom of the ramp where the height is 0? For this problem, we're going to ignore friction. So we know that due to the conservation of mechanical energy, the total energy initially is equal to the total energy finally. So we know that mgh initial plus 1/2 mv initial squared is equal to mgh final plus 1/2 mv final squared. Since initially the velocity is 0, and at the end the height is 0, we can say that mgh initial is equal to 1/2 mv final squared. Now we can plug in our values and solve for v final. And we get that v final is equal to 20 meters per second squared. In reality, the mechanical systems we study can lose energy from things we call non-conservative forces. These non-conservative forces don't destroy the energy, but they do transfer it out of the system. The most common examples of non-conservative forces are friction and air resistance. Friction opposes motion and transfers kinetic energy into thermal energy in the form of heat. A great example of this is rubbing your hands together rapidly. When you do this, friction is transforming kinetic energy from your hands into heat. In our problems, we will often only consider conservative forces acting on our system, and thus total energy of the system is conserved. However, it is important to keep an eye out for when a non-conservative force might be acting on your system. In the real world, friction and air resistance are almost always acting. This takes us to the concept of efficiency. Because non-conservative forces are almost always acting on a system, the energy you put into a system is almost never equal to the energy you get out. So efficiency is the ratio between these two energies. Efficiency, often abbreviated as the Greek letter eta, is equal to the energy out divided by the energy in. If you have high efficiency, then the energy you get out of the system is a large fraction of the energy you are putting in. If you have low efficiency, then you are getting a small fraction of energy out from the energy you put into the system.